In this video, we're going to take a look at the enthalpy change for a reaction, this reaction being the combustion of propane through three different lenses. We're going to take a look at the energetic properties of it through calculating bond energies, heats of formation, and Hess's law. So the enthalpy for a reaction is essentially the heat change associated with it, and it tells you basically how exothermic or endothermic a reaction is. So taking a look at bond energies, when you have a chemical reaction occurring, really you have a few things going on. You have bonds breaking and you have bonds forming. So bonds breaking is an endothermic process, meaning it requires the input of energy. So if you take a look at even for an exothermic reaction like the one we're talking about here, because clearly energy is released when you burn propane, like in a grill, energy has to be put in, and we call that the activation energy. But really what the activation energy is the energy to take the bonds that are currently present in the molecules and break them up so that the new bonds can form. And then once new bonds are formed, energy is released. And this process should make sense based on which one requires energy and which one releases energy, because we know that anytime you have two objects that are attracted to each other, like the atoms in these bonds here, and you try to separate them, it's going to require an input of energy. And whenever you let two objects that are attracted to each other become closer together, there's actually a release of that potential energy. Just like when you drop an object, it's going to get closer to the ground and it releases energy when it does. So if we take a look at this reaction, the bonds that break here, you have 8 carbon to hydrogen bonds, and you have 2 carbon to carbon bonds, and then you have 5 oxygen to oxygen double bonds that need to break, that are currently there within the reactants and that aren't there when we look at the products. And then you can see that the energy required to break all those bonds is about 6,500 kilojoules. And then the energy released when the new products form is you have essentially, because you have 3 carbon dioxide molecules, you have 6 carbon to oxygen double bonds, and then with the 4 water molecules, you have 8 oxygen to hydrogen bonds that form, and you get about 8,500 kilojoules released when the new bonds form. So if we look at the energy for the reaction, since the bonds being broken requires an input of energy, we would give that a positive value for the energy there, and then the energy released would be negative. You can see that this releases about 2,000 kilojoules of energy. If we take a look at this reaction through the terms of heats of formation, which is essentially an extension of what we're going to learn about in the next slide called Hess's Law, we're going to use heats of formation. So it said for the enthalpy change for a reaction is equal to the sum of the heats of formations of the products minus the sum of the heats of formations of the reactants. And the heats of formation is the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. So basically what they are at room temperature. And you can see here is a table, and you can look these up. The enthalpy of formation for each of these things. Anything that's an element in its standard state is going to have a value of 0, so we can actually omit these from the equation. So for example, when we look at our reaction, propane plus the 5 oxygens, the oxygen is an element in its standard state. So forming the element from its component elements would really not be any change at all. The other 3, however, we have to look at. So for the product side, you have 3 carbon dioxides forming, and you can see from the table that this is the energy associated with that, plus 4 waters forming. You can see the energy change associated with that, minus the heats of formation of the reactants, which would be just the propane, and you can see that that's subtracted here. And again, you get about 2,200 kilojoules of energy associated with that. And then, like I said, the last slide really just is an extension of Hess's law, which states that the net enthalpy change of a chemical process is equal to the sum of the enthalpies of the component reactions that combine to yield the net chemical process. Basically what that means, if we can get reactions to add up in a way that the excess stuff that we don't need in the net chemical equation cancels out on each side, and we add up the reactions and they add up to the net reaction, the energy of each of the component pieces is going to add up to give us the overall enthalpy of the reaction. So we can see here that these 3 reactions, you have carbon plus hydrogen to form propane, you have carbon plus oxygen to form CO2, and hydrogen plus oxygen to form water. These are really heat formation reactions as well. But you can see that given these written the way they are, if we want to get everything to add up to our net reaction of propane reacting with oxygen to make CO2 and water, we would have to flip this first equation, because propane right now is on the product side of this reaction, and we need to get it on the reactant side. whenever we flip a chemical equation, what we're essentially going to do is change the sign from, in this case, negative to positive. If it was positive, it would then become negative. So when we flip it and rewrite it, we can see that the energy is just represented as a positive value. In this next reaction, what we have to do, since carbon dioxide is on the product side, which is where we want it, we don't have to flip it. However, we need to make 3 moles of CO2. So we're going to multiply the heat of the reaction, heat of formation here, by 3. And you can see that when we do that, we get that for a value for the enthalpy change there. And then we do the same thing with water. Water's on the product side, just like we want it to be. But we need 4 of them. So we're going to multiply this whole process by 4. When we write out these 3 equations that we have here, what we can see is that you're going to end up canceling out things that don't need to be there. For example, there are 3 carbons on the product side here. We don't need those because they're not in the net reaction. There's also 3 over here on the reactant side. So when you add up these reactions, those go away. We also don't have any hydrogen gas in our net reaction. So if we look, we can see that our 4 hydrogens cancels out because it's both present as a product and reactant, and therefore we can get rid of it. And then you can see that in order to get the 5 oxygens, when we add up these 2 values, we get that as well. So you can see here that these 3 processes, once the reactions have been manipulated as we have done, you can see that they add up to the net overall reaction. So really, Hess's law basically says that for enthalpy changes, which are considered state functions, it doesn't matter how you get to the end result, whether you looked at it through bond energies or heats of formation, or you added up different reactions in Hess's law, the energy change is the same. And you can see that for all 3 of these reactions, you got about 2,200 kilojoules per mole for the combustion of propane.